למעשה, שתי הצעות במחקר היו בגלל שהיינו צריכים להתמודד עם כל מיני תוצאות קומבינטוריות של יחסי אנגל. עכשיו אנחנו בעצם ניגשים לעצם הטיפול בחברת אנגל. אנחנו כרגע... Sorry, I have to go in English, I'm sorry. We now, 2.5 lectures we just had, we dealt with combinatorial properties of angle relators. Actually, it could be very easily summed up because the angle relator have many partial symmetries. And when we have two angular relations, not of the same type, then their symmetries are incompatible. Actually, everything we have done for this is just how to specifically use this incompatibility. It could be done this way or that way. In any case, we're done with this. So we know that there could be only less than 16 letters of the bigger type on the boundary of the smaller type. Okay, now let us assume that we take n equal to 40. N actually, when I need to reduce to 1 or 2, so actually it will be 41, 42, but we now already assume that all our angular letters are cancelled and that A is bigger than B. So just, it means that actually we take bigger than 40, but now without loss of reality, we assume that A and B do not cancel out anymore, and that A is 8 times bigger than B, for example, at least 8 times. So B may be very small also, but it could not be bigger than this, because we can redouble, do A until we get this error. So now we take the angular relators and we divide them in two levels. The first level will be when the length of A is between 1 and 2 to the power 10. The second level will be when the length of A, the power 10 plus 1, between 2 to the power 10. It means that the level number K will be when 2 to the number K minus 1 times 10 plus 1 less than equal A less than equal A without K. This is the level, this is the level K. This is the level K of the slice K. Okay, now let us first consider the first level. So we take R1, all the relators, A, B, B, 40 times, when what we know is that in each cyclic word, the number of A's will be precisely 2 to the power 40, half a billion. And the numbers of B also the same. Now, what we can conclude from our previous reasoning? If we take the shortest one, which will be xy 40 times, and if we take the biggest one, cd 40 times, when we know that the length of C is less or equal to 2 to the power 10. So we might have here less than 16 such C's. 16C will be 16c less than equal to the power 14. So we have on this side, by the way, from now on, we are counting, our measure will count only the A's but not the B's.
Only the A's but not the B's?
Because this word is composed A, B, etc. And A is at least 8 times longer than B. We just skip the B's and only take the length of the A's. We see why it is convenient to do this way. In any case, so the length of here will be no more than 2 to the power 14 out of 2 to the power 14. So we see that after all, taking the extreme case, the shortest relation from the first level with the longest relation from the first level, there is still a very small part of the small relation. Okay. So in this sense, it will satisfy the small cancellation condition. Have many. Now, let me say the following thing. Actually, we will take the following relations. We have described that some of these could be glued in the following way. If the velocity A, B, so let me remind it. This was some word we call the T2 of AB. This was the word T2 of AB. T2 of AB and T2 of AB. This is just cyclic word corresponding relation. Here we had what we called B placed to the 0 place. B1. This index only says what is the source of this B. And B0 is the last B in this, and B1 is the one previous. Now, but here this is now what will be very important. That actually we can take any power alpha here and any power beta. So alpha and beta are integers. Because this is a way we can glue them together. Otherwise, this is just commutative lines. So actually, we will take not only these relators, but also all these. But because we are measuring only the length of A, it doesn't matter. This is, by the way, this is the reason I prefer to take only look on the length of A's. This may be a very big power, but in our measure, length measure, it is not counted. We take only the relative length of the A's inside the bond. And then it is a set, because then precisely when it happens, it doesn't matter. Okay. Now, we will do the following. We will define the set of forbidden words. So what we're going to do? Now, we are looking on the group AG1. This is F divided by the first level of relations. This is the rank 1 case. We would like, for example, to have a canonical word here. Presentation of this element in a canonical way by words. And then also we would like to have the canonical form of all cyclic words and the canonical form of all angular relators, which big rank which is imposed in the cycle. So let us start with this. The first thing that we are going to define a set of forbidden words. So we do it in the same way as before, taking 0 here, 1 here, a half. So, and we have actually 4 levels. Number 0, number 1, number 2, and number 3. But now we assume that all of them are very close to a half. When we looked on small cancellation in general, we assumed they are somewhere about 2/3. Now we think of the constants lambda 1 bigger than lambda 2, bigger, actually lambda 3 bigger than 1/2, close to 1/2. I mean close in the sense because our epsilon is very small, something like 2 to the power 26. And then we take it very close to f. Still widely separated in the terms of epsilon. Widely separated.
Professor, so we are interested only in the cases of any groups with large enough n, right? Like we...
Of course. Actually, we will not do any attempt to minimize n for any groups.
Of what?
We will not do any attempt to minimize the value of n for any groups. It could be 400 as well. It could be the interest question in itself, the minimal, but now we are definitely not trying to do it. So we will take it as big as convenient. In the terms of epsilon. So many epsilon between them. It's so small doesn't matter. And this is actually very close. It is very close to half, much less than 3/4, etc. But in any case, so then we just as earlier, we define a word lambda semi-canonical if it doesn't contain more than a lambda of a letter from this group. So, a word is lambda semi-canonical if doesn't contain more than lambda of a relator. Is from in this case from R1, but we're dealing now with a case rank 1 case. So semi-canonical, if you wish, in rank 1. Now, then we have to ask the same question that we asked before, to ask what are the semi-canonical words representing a given element of G1. G1 is f over f1. Let me recall that in the case of small cancellation groups, we obtained the one layer array. This was the answer. Then, here, basically, for the same reason, we obtain the same answer. Because the argument doesn't change. We see the chart. We consider the one chart. Then we can take the, we obtain one layer as before. Starting with the one chart of the given representative, and then the alternative will be, because of everything of matter, this is epsilon is small. Just the same geometric reason gave us exactly the same conclusion. But here happens something very interesting. For example, it might be that this is some particular element of the one chart. So I can match it on the relator. And just maybe more contrast color. So we don't have, let's be green because both of them are green. And assume that it goes, for example, this way. In this way, it does not exceed half by much, because this is a half, because each of them is a quarter. So it is a quarter and some two additions, so that it could be inside these boundaries, not much bigger than half. So what will this mean? Let me say, just we can picture it. Here was this side of it. Then we have here b to the power alpha, right? Then we have here b to the power beta, and here we had b to the power alpha. And what's in between? Here we had what we call 2t2 of A and B. It was in this direction, and also here we have t2 of A and B, and this is just initial segment. This is an initial segment of T2 of AB on one side and initial segment of T2 on the other side. This is an example was condemned. Now, here is the following important thing. Alpha, we can substitute alpha by any integer or gamma. It will represent the same element. Why? It is actually obvious, but because the fact I could explain explain it here.
What is it you do? Ah,
It was a pattern.
This is I. So assume that we have this way. This was, we had this way, b to the power alpha. Here we had b to the power alpha. Here we had b to the power beta. Now, here we can add, so let me say, this was T2 of AB, this was T2 of AB. Assume now we add b to the power gamma minus alpha, b to the power gamma minus alpha, b to the power beta. This is T2 of AB and T2 of AB. Just adding to this.
one more. What is it you do?
Got it. Let me see. When we describe the combinatorics of angular later, so we observed in the following way. They will follow what is the position of the numbers of this in this relator. So this will be number 0, number 1, etc. So B coming from this sits in two opposite situations of this. The one will be sit here, B2 will be sits here, inside this. Now, and then it will be oriented toward the smaller one. Now, then inside here we have the B3 and B3. So, what happens? We say that our angular relation is this, then we will say that T2 of AB is actually T, it will go, T3 of AB, B2, T3 of AB inverse. And this in general, we have Ti of EB equal Ti plus 1 of EB, B in the position I, Ti plus 1 inverse. So this is the recursive equalities that define the structure of the angular relator. Each next one is a pair of this, it's a B, and this part goes here. This is a kind of structure of this relator. So T2 is the second one. The second one. Because the first one was just B0, and here we have T1 of AB on one side, and T1 of AB on the other side. So actually we have T1 is roughly half of the relator. T2 is a quarter of the relator. T3 is 1/8. The mnemonic is 2 to the power I. 2 to the power I is 1 to the power of the relator, except of the letters of BZ.
Okay, yeah. Now I understand.
Okay, so actually this is a relator. So and then we have this wall here. So let me look at where this was. This was our output. This was what we call the element of the chart. and we have it here. Now, when we add this, so we are in the same, this represents the same element of the group, because it's equal to one mod of the relations. But what we have now we will have where I should edit, probably I should edit, excuse me. I should edit, it doesn't matter, on this type, on this side. Okay? And then we have here b to the power gamma. So we just, it means that we can modify this parameter to any integer and representing the same element of the group, G1.
Yeah, but also your measure doesn't care about the bees, right? So
Therefore, the mesh doesn't matter. So therefore, it was semi-canonical, it remains semi-canonical. So these are different semi-canonical words representing the same element of the group. They are different by an integer parameter. Okay, so of course, when this particular situation happens, if this member of the chart just happens to at least touch two of these opposite B's, then we can generate a family of semi-canonical words that are depending on an integer parameter. And this is different from the situation we had previously. Because then in the one layer map, we only had situation, the word of its complement. Here we may modify it by integer parameter. When it happens, when both of them are on the same side.
So in some sense you have more than one turn, like it's not turns. Before we had turns, right? Like the
No, yes. Now what we can here happen here, we can modify. Now enters an integer parameter. Good. Why we cannot have two integer parameters? Because we stipulated that our constant is much less than 3/4. If we would allow 3/4, then we would have such a situation. And no, still, yes, then both of them are inside this map, and then we have two integer parameters. So actually it would be depend on a z times z. But because we assume that our parameters are close to 1/2 and definitely less than 2/4, we just excluded the situation. Okay. Now, actually, we can even say more. We can also consider this in literally as a one-layer map, but we have to mark the positions of this middle beta. It could be, for example, here and here for one of them, and here for the other one. Whatever. And then we have here this is the number of two integer parameters, but inside this word. Because all of them is just model of this relation. So we do have a one layer map, but when we have situation, so we might modify them by any integer the powers of this equation, and they will still represent the same element in the group. And when we forget the y's, remember the a's and the b's, and remember only the a's, then actually they are presented by the same one layer map. But now we differentiate each cell here could be depending by two integer parameters. Okay. Now, in any case, given this situation, we still may do our previous constructions literally. I mean, what we've done, we have defined the certified one-layer map. So, how we have done this? Exactly the same thing. That we ask whether this or this, whether any particular side of the one-layer map belongs to the certified one-layer map. When does it belong? When it has a witness that certifies it.
Sorry, insurance company called me, sorry, ahead. So you are talking about downside situation.
No, exactly. But I'm saying that it, with one important difference, it is identical. What is the difference? Because here the relations have this B's that could depend on an arbitrary parameter, integer or power. Because this could be changed arbitrarily. So actually it means this is not one layer map. It depends on for each cell by a pair of integer parameters.
So it's not one layer map. Sorry again, it's not one.
Because we consider, so what we started with, let's say, one node. We looked on all on the one chart of it, all the maximal appearances of subrelators. And then we can take also, when it is appropriate, we can take also their inverses, I mean the complements, just as we take in the Bernstein case. But now, if we forget the B's in this, then they will be the same. But they may be different. We can modify them by taking two different integer parameters inside every cell.
Why two parameters?
Because one for alpha, the other for beta.
But you can change only alpha by.
Oh,
Your
yes.
complement depends only on gamma that we can add to alpha.
Yes. Now, if we would try to change this, actually we will change the vote. But saying inside this one layer map, we can change both parameters. But what I'm saying is that we can verbally take the same definition of a certified map. When it is certified, when we have a witness, when a particular site is certified, and there exists a witness, the witness itself should be inside this map. Here it should be on each side of it, and then when we look on the rest of the numbers of the map inside the witness, then it should satisfy the appropriate inequalities. For example, for this one, we set less or equal to lambda 3. The next should be less or equal to lambda I of 1, say rho of 1, less or equal to lambda rho of 2, etc., where we fix some sequence of numbers, rho 2, etc., all of them belong to 1 and 2. In the case of Bernstein group, we assume that this sequence is aperiodic. Here, we assume it is biperiodic. It cannot follow, in the case of the angular with two biperiods, it cannot follow the regularity of the angular word more than a fixed number of periods, and no more than, say, 5 periods. And it is easy to organize such a sequence.
Sorry, what's the B periodic?
Because the B periods of linear meter. So we assume that we can choose these numbers. So this sequence could not sit more than in 5 B periods of a Gilbert. Or 16, whatever we wish, there's some fixed number of periods. So this we insert in the definition of a witness. Let me remind what it was. Now, we say that a side in this one layer map is certified if it has a witness of it. And when the witness, it is some word here, it satisfies the number of restrictions of the relative length of the word. It would be no more than lambda 3 here, which is the most stringent, and then no more than lambda I1, lambda Y2, etc., on both sides, just as we had done the previous time. Because it doesn't matter, because actually the parameters, the powers of the cancel out, because we count only the ace. Okay, so we have the same definition of a certified map. So from now on, we look on the certified map. Now, when we look at the certified map, we will do this the following. Actually, if we are not in this situation, the touch at least both of them, it may be go this way, but no more than this. Then the word itself will fix the parameters of this. Because if it touches 2 times of the same B, then we can modify it. If it doesn't, then the word will fix these parameters. And then the opposite also will be. If it exists in a certain way, we'll also fix it. 2 on the side, 2 on one side, 2 on the other side. It couldn't be 3 on one side unless situation. And that's the other will be just fine. So, in all except this situation, we consider as a hyperbolic situation, because it has only 2 alternatives: to take the word or its complement. And then we have to decide which side to take, and we actually do a local competition in the way that we did it before in the small cancellation case. By the way, because even their neighbors may be with parameters, but no, their neighbors with parameters, if they are certified, then their value of parameter doesn't influence the outcome. Because we count only the a's, and so for them we can define what side of the case just as a previous situation. It's not verbally without changing it. But here with the entirely other situation, when we have these things that may have these parameters. Now, when we have these parameters, we may imagine, for example, immensely big. So actually it looks this way. Something here, then, excuse me. Instead of this now, we have a very, very big power of B. Then we have the same situation. We have T2 of AB. Then, the same that we had earlier, T2 of AB. Then we by the same extremely big power of V. Or it could be this way, whatever. Now, we deem these as flats. Because actually we could take the same, where to cross it depends just by us. We can cross it in this way. The crossing is the same, always. I mean, the same word. T2 of AB, here it is T2 of AB, and here we have B to the sum our beta in all cases. But this will be variable. So now, then we have, so how we look at it? So the rest of them are already chosen, but here we have a situation where we have one flat, then we may have another flat, then we may have another flat, etc. Now, here is a situation. It might happen that two flats can, this might be trivial word. But it could be that this corresponds to the relator A1b, and this corresponds to the relator A2b, with the same b, but with different a's. Then we have here a power of b. This word will be trivial, then it will be also this, they will be come together. So the glue, we may glue together the flats when there is a word, there is a trivial word that connects. But it may be a situation that we cannot glue them together, even if it's the same B. But then the question is how to choose the word between them. Instead, we would take this word, for example. Now, then, very simple. If we take it in an arbitrary way, and we take the cancellation. We can, so let me fix it in any way, and then it cancels out, Then this procedure will not depend on where we started. We just have the same way, so just in the same word after cancellation, it will be in some definite place. So what will be the final picture of it? The final picture, we have the board. This hyperbolic sign already chosen, and then we have a number, this may be a composite flat. Now here we have some other, maybe a composite flat. Now we have a different composite flat, and it goes this way. What happens? The flats could be crossed in different places, the same way. So actually I have situation. I can go cross it this way. Then I have to go to here when it touches, cross it this way. Go to this, cross it this way, and then this is one way to do it. But there is another way to do it. I can start doing it from the opposite direction. I go in here, I'm crossing it here until I can. Then I'm having to go here. I'm crossing it here. I have to go right here. I'm crossing it here and go this way. So actually there are, depending on the side, I have two different ways to do it. So I starting from the left to the right, I cross it at the first possibility, and then I have to go to the path connecting them, cross at the first possibility, etc., etc. Okay? Doing the opposite way. Starting here, cross at the first possibility, go to the connecting path, cross it, etc., etc. So what to do? Here is the following. When we have two possibilities, actually it is right to taking a canonical form in Z coset. Because here's our flat. Here it touches here, it touches here. So either we will go this way, or we will go this way. So actually this is just two parameters. I mean this is Z and Z. So the question is what of them to prefer? The answer will be like if we have so we have to see B, some power of B, and then crossing this. If the power of B is positive, we will cross immediately and then go. If the power of B negative, then we first go to this point and cross this.
So in some sense,